Hi, in this video we are going to talk about Radix sort, so let's get started. Radix sort can be very efficient because there are no comparisons, and that's why I start with this sentence, because we have talked about merge sort, quick sort, bubble sort so far, and both of these algorithms are relied heavily on comparisons. We keep comparing characters with characters, whether character A is less than or greater than character M, for example, whether the number 7 is greater or less than number 4. But this is not the case here. It is a non-comparative algorithm, and that's why we can do better than ordo n log n, because there are no comparisons at all. And that's why this algorithm has a running time ordo k times n, where n denotes the number of items you want to sort and k is the number of digits in the input number. And we have to consider then, if k is a very huge integer, then this algorithm can be worse than bubble sort. So this is not the best case, but the average case is very fast, and we can perform even sublinear time complexity. So we just sort the elements according to individual characters, and it's very important that it's a stable sort too. It has two main types, the so-called LSD and the MSD string sort. LSD stands for least significant digit first string sort, and we consider the characters from right to left. We start at the least significance digit, and that's why the name. So we can use it to fixed length strings or fixed length numbers, for example integers. We just sort the characters at the last column, then keep going left and sort the columns independently. So it's kind of a typical interview question that we have 1,000,000 32-bit or 64-bit integers, and what's the best way of sorting them? And I think most of the candidates has a guess of merge sort and quick sort or heap sort. These are the known fastest sorting algorithms, but the right answer is the Radix sort. So it's quite an important algorithm. MSD stands for most significance digit first string sort. Consider characters from left to right, so with the most significance digit, and that's why the name is MSD. It is sensitive to ASCII and Unicode representations. For example, it's very important because if we optimize or Radix sort to ASCII characters, then if we, for example, in Java code change to Unicode, then these algorithms can be very slow. So this is the main disadvantage of MSD string sort, and it has several advantages of course too. MSD examines just enough characters to sort the keys, and as we have seen with ternary search trees, it is a very good optimization. That's why ternary search tree performs better than hash table, and that's why MSD performs better than LSD, because it examines just enough characters. So can be sublinear in input size. It's very important. So MSD access memory randomly, which is not so efficient. So there are, we have seen so far that there are for every algorithm, sorting algorithms, even for merge sort and quick sort and Radix sort, there are some advantages and some disadvantages, and that's why the scientists came to the conclusion that we should combine it, the Radix sort, with quick sort, and this is the so-called three-way Radix quick sort, which is quite fast, and it's try to eliminate the disadvantages of both these algorithms. So let's see the LSD Radix sort algorithms. We have number to be sorted, and we have buckets. It's kind of a bucket sort. The buckets represents the 0, 1, 2, 3, 4 and so on up to 9. It is just the characters, and we start from the least significance bit and we just consider them, and we keep putting these numbers into the given buckets. We keep putting the 120 into the 0 index bucket, because the number with red is 0. The next one is 0, 2, so we keep putting there, then 9, then 1, then 5, then 5 again, Then the least significance bit is 3, so we keep putting at the index 3. then 1, and yeah, that's the last number. We have to clear the original list and construct it again. As we see, we can do it with linear time complexities. We can do this, construct these buckets with linear time complexity, so it's going to be a linear time complexity algorithm. And we keep pushing back, I mean popping these numbers, and keep reconstructing our arrays to be sorted like this. And here we just want to we go on and we sort according to the next digits. So yeah, because we push it to the index 2 because it's 120 and the middle number is 2, so okay, 4, 7, 2, 7, 5 and 8. Okay, then we keep putting back in this order, so it's very important that we start from bucket 0, then 1, 2, 3 up to 9 and keep getting the items. Okay, then go to the next index and do it again. So I think it's pretty straightforward what's the algorithm, and we keep constructing the number to be sorted again, going to the next index, building the buckets, I mean filling the buckets, then go to the next index, filling the buckets too, and then building for the last one time, and as we see, then it is perfectly sorted. So we constructed an algorithm that can outperforms, can do better than merge sort and quick sort, and we can do it in linear time. This is the so-called Radix sort, and it's very, very important. For example, in DNA sequencing, that was the problem. We try to sorting the suffixes of the DNAs, and we can do it in linear time complexity with the help of Radix sort. Thanks for watching.